A resistor and an inductor are connected in series along with an EMF source of constant voltage. So this is an RL circuit. The circuit starts at t equals 0. The switch is closed at t equals 0. At t equals capital T, the current in the circuit is 4.2 amps and the rate of change of the current is 22 amps per second. That's a positive rate of change. On the other hand, as t goes to infinity after a long time after the circuit started, the current becomes 12 amps. That is the final value of the current when it becomes steady and it stops changing. The question is, what is capital T? The current in this circuit changes with time and it can be formulated as maximum value of the current I sub m times in parentheses 1 minus exponential of negative RT over L. So this is the formula for the current in a RL circuit with growing current. Again, I sub m is as the maximum value of the current, which is the value it gets after a long time the circuit has started, which is given in this problem, 12 amps. And R is the resistance, and L is the inductance in the circuit. So those are not given, but we can actually calculate them using the other information in this problem. So this is the formula, this is the expression that represents the current as a function of time. Now, the other piece of information that's given is di dt at the same moment. Let's actually come up with an expression for di dt. Let's take the derivative of this formula, see what we get. Here's what we get when we take the derivative of I as a function of time. Di dt, rate of change of current, is basically the same expression as current, but we get a factor of R over L because the derivative of exponential is itself, but then we need to multiply it by the argument, by the coefficient of t in the argument, which is negative R over L. There's another minus sign in front of the exponential, so those negatives cancel, we get this expression. So now what I'm going to do is I'm going to divide these two equations side by side to get a ratio of I divided by di dt. We'll see that a lot of the variables will cancel and we'll end up with a simple expression. Here's what we get when we divide the two equations side by side. The ratio of current divided by the rate of change of current is equal to capital L over R. So now we can actually calculate this ratio for t equals capital T because those values are given. At that moment, the current is equal to 4.2 amps and the rate of change of current is 22 amps per second. So we can calculate the left-hand side numerically and come up with a value for L over R. So numerically we get L over R equal to 0.19 seconds. Note that this is also the time constant of this circuit. Now let's go back to the formula for the current as a function of time and calculate capital T. Here's our formula. I substituted capital T for the time variable. And next I'm going to rearrange my formula to isolate capital T. First, let's divide both sides by I sub m, the maximum current. Here's what we get. Next, let's rearrange the equation to isolate the exponential term. Here's the exponential term isolated. The next step will be to take the natural log of both sides so that we get rid of the exponential term. Remember, what we're trying to do here is to isolate capital T on the left hand side, and it's in the argument of the exponential. So that's why we need to take the natural logarithm of both sides so that the exponential disappears from the left hand side. Here's what we get after we take the natural log of both sides. Now, as the last step, let's divide both sides by R and multiply both sides by L to isolate capital T. Here we have capital T isolated. We know everything on the right hand side of the equation. Now, we haven't calculated L and R separately, but we have calculated the ratio L over R, which is equal to 0.19 seconds. On the other hand, the value of the current, the instantaneous value of the current at t equals capital T is 4.2 amps. That's given in the problem. Maximum current is the current when t goes to infinity. That is also given, 12 amps. So we have everything on the right hand side. We plug in the numerical values and calculate. We get capital T equals 0.082 seconds. So this much time later, after the switch was closed, the value of the current becomes equal to 4.2 amps, and its rate of change becomes equal to 22 amps per second as given in the original problem.